So now we'll look at the technology developments that we've covered during the work that we've done at SPR Limited. And these actually cover 4 generations of technology. And to be logical, we will start with the first generation. Now, this first generation technology essentially uses ambient temperature copper or silver plated alloy cavities, and we've used them both for experimental and flight thrusters. So although it is actually only the first generation, there are still some very important applications for these flight thrusters. These include what was originally the requirement, if you like, the driving reason for EmDrive development, which was orbit raising for large geostationary communication satellites. Therefore, first generation can be used for primary propulsion, and also for attitude and orbit control for all satellite types. An interesting application is the low-cost thrusters that can be produced for the small CubeSats. We can use first generation for science probes, and one other particularly important application that's arisen during the work that we've done is for a space tug. This is where we use high power S-band thruster for a number of future applications for a space tug. Typically, the operating frequencies for first generation thrusters range between 2 gigahertz and 4 gigahertz. The input power range, we've produced designs covering 40 watts to 10 kilowatts. Specific performance, this tends to be between 300 millinewtons per kilowatt and 500 millinewtons per kilowatt. It depends essentially on the frequency, the size of the cavity, and the temperature at which it operates. But I guess one of the most important things about the first generation technology was that it was actually proof of concept for the whole EmDrive concept. So now we'll look in detail at a first generation CubeSat, and this is a 12-unit CubeSat. That refers to the size of the satellite being essentially 12 10 centimeter by 10 centimeter cubes. They are configured as a 2 by 3 arrangement. The cavity for this small CubeSat had to be reduced in size from the original flight cavity, and so what we did was to use a TE113 transmission mode rather than the TE013 mode that we used for the flight thruster, but we retained the 3.85 gigahertz frequency. This resulted in a cavity design with a large end plate diameter of 150 millimeters and a small end plate diameter of 48 millimeters. Particularly important for the CubeSat was the radiative cooling that we used to reduce the in-orbit operating temperature of the cavity down to minus 75 degrees C. This was achieved mainly through the thermal panels, which you can see are deployed from the base of the satellite structure, and they're kept in shade continuously by the solar arrays, which are deployed from the top of the satellite. There is also a small sun shield deployed at the large end plate end of the thruster. This is to keep this end plate in continuous shade, because that is really where most of the thermal dissipation from the thruster comes from. So this combination of sun shield and thermal panels enables the temperature to be kept down to -75 degrees centigrade in the main flight configuration of the satellite. The lower temperature, the lower operating temperature, more than compensated for the smaller size of the cavity, and we got a resulting Q of 84,000, which gave a thrust of 20 millinewtons for an input power of 40 watts. So this is a specific thrust of 500 millinewtons per kilowatt, compared to the flight thruster specific thrust, which was 326 millinewtons per kilowatt. So the overall dimensions of the satellite then become 30 centimeters by 20 centimeters by 20 centimeters, and we did a mass budget which arrived at a total satellite mass of 20 kilograms, which included a 6 kilogram payload. A rather larger first generation design that we've been working on is one for a space tug. And for this, we have a 2.45 gigahertz TE015 cavity with a major diameter of 310 millimeters, a minor diameter at the small end plate of 151 millimeters, and an overall length, internal axial length of 426 millimeters. This is to cope with the 5 half wavelengths of the TE015 transmission mode. The cavity that you see in the photograph was our experimental cavity, which in this case was powered by a small commercial 800 watt magnetron, which you can see attached to the input flange on the side of the cavity. The flight thruster itself is designed for a 10 kilowatt magnetron source, and the flight thruster itself would be mounted in a two-axis gimbal mounting. If you look at the diagram at the lower right of the slide, you'll see that the space tug itself is mounted on the end of a spar, which forms part of a 3.6 kilometer diameter sunshield, orbiting sunshield. The space tug can also be used for attitude and orbit control of a solar power satellite, but in this case we've got it attached to the sunshield. The space tug itself has body dimensions of 0.8 meters by 0.8 meters by 2 meters long, and it deploys a 16 panel solar array, giving something like 16 kilowatts end of life DC power. There is a thermal radiator deployed from the base of the space tug, This is 1.8 meters wide by 6.2 meters long, and it uses an active freon cooling loop to maintain the low temperature required to get the performance from this first generation thruster. The performance is a minimum thrust of 5 newtons for the 10 kilowatt magnetron input. Total mass of the tug is 784 kilograms. So it's a pretty substantial spacecraft in its own right. Second generation EmDrive technology uses superconducting internal walls within the cavity itself to dramatically increase the Q of the cavity by significantly reducing the resistivity of the walls themselves. In fact, you can get huge increases in the Q of a superconducting cavity compared to a non-superconducting cavity. And this in turn gives huge increases in the specific thrust for the sort of applications that we're going to look to for the future of EmDrive. Now, the big problem is that these large increases in Q cause significant Doppler shifts in the internal electromagnetic wave when you actually accelerate the cavity itself. And we need to look at this in detail by looking at the diagram given in the left of the slide. Here we can see that we have a standard EmDrive cavity where the guide velocity Vg1 at the large end, which is significantly greater than the guide velocity at the small end Vg2. And it is this difference in guide velocity that gives us the problem with EmDrive cavities when you accelerate them. And to see how this happens, we need to determine what the transit time for a wave to travel from one end of the cavity to the other is. And we've defined that as Ts equals P over 2f0, where P is the number of half wavelengths and f0 is the resonant frequency. Now we need to look at the forward and reflected frequencies, and to do that we need to determine the velocities at the reflection of these two transits. And we determine that the velocity of the cavity itself, Vf, at the small end is Vr, the cavity velocity at the reflected end of the large end, is therefore Vf equals Vr plus A times Ts, where A is the acceleration of the cavity itself. To look at the actual forward frequency, FF, we need to solve the equation that we give here, where FF equals FR times the term in the square bracket, which is 1 plus VF over VG1 divided by 1 minus VF over VG1. Similarly, we can calculate the frequency for the reflected wave, which is FR. And if we take the difference between FF and FR, we get the total Doppler shift for one transit forward and backwards of the electromagnetic wave. Now, in a symmetrical cavity, we don't need to worry about Doppler shift because In fact, in this case, Ft is equal to minus Fr, and the two Doppler shifts cancel out. But with an EmDrive cavity, because we have a difference between VG1 and VG2, we will get a significant Doppler shift, which will cause a movement away from the resonant frequency of the cavity itself, and therefore cause a reduction in thrust. Our experimental second generation thruster was constructed using IBCO thin film superconductors on flat sapphire substrates, which were in turn mounted on Kovar carriers. IBCO is yttrium barium copper oxide, which is the standard so-called high temperature superconducting material that's readily available commercially. However, it is only commercially available on flat substrates, and these are nevertheless pretty expensive. I think the total substrate cost was well over £10,000 for this particular thruster. The flat substrates mean that you have to design a rectangular tapered cavity rather than the normal circular cavities that we've been looking at up to now. And we designed it around a resonant frequency of 3.83 gigahertz. If you look at the photograph, you can see the rectangular cavity is hung from a lid which fits into a vacuum walled dewar which contains liquid nitrogen. So we totally immerse the cavity itself in the liquid nitrogen, which brings the temperature right down, and we actually measured a Q value of 6.8 by 10 to the 6. So this is about 100 times the Q of the flight cavity, and we were very well pleased with the with this Q. It was slightly better than we'd predicted. What we didn't predict, however, was what happened when we put power into this thruster in an attempt to measure thrust. And as soon as power was applied, very small number of watts, we suffered the substrates themselves cracking due to the internal stresses within the thin films on the substrates. The substrates themselves are extremely thin, about half millimeter thick, and they're very fragile actually. And what happened was that the mounting between the substrates and the Kovar carriers was not robust enough to stop the thin films from cracking, which was all a disappointment, but it did indeed show that we could get the very high Q value that we were looking for. And we produced a mathematical model based on a theoretical Q of 3.7 times 10 to the 6 to look at what the Doppler shift would mean in terms of specific thrust against cavity acceleration. And you can see that the result is given in the plot on the right of the slide, and it's a modest loss that we can actually live with as long as the Q is of this fairly low order for a superconducting cavity. If, however, you were to take this cavity and cool it with liquid hydrogen, the resistivity would go down significantly, the Q would go much higher, and the Doppler shift would start to get very much more significant, such that we would need to look to compensate for the Doppler shift itself. We have proposed that we can demonstrate second generation technology by flying a very small UAV, unmanned aerial vehicle or drone, basically using fixed thrusters and liquid hydrogen cooling. The fixed thrusters mean that we would use standard drone flight control system, and the four thrusters themselves would be operated at 2.45 gigahertz. They'd use solid state power amplifiers and batteries. The liquid hydrogen would be carried in a 50-litre tank, which is enclosed in a foam body shell to provide some insulation to reduce boil off. And we've predicted a specific thrust of 463 newtons per kilowatt. This is for acceleration limited to only 0.05 meters per second. So it's going to be a pretty slow vehicle, but nevertheless, there's enough thrust there for it to lift off and fly. The demonstration flights would be limited to a maximum range of 1.6 miles, and therefore the vehicle would remain in line of sight, and we'd have to keep it below 400 feet to meet the flight regulations of the range that we propose to fly this in. Maximum velocity, we'd get up to about 11 miles an hour, limited of course by the very slow acceleration that we can get. And a maximum flight time of 12 minutes is limited by the amount of liquid hydrogen we can carry and the charge in the batteries itself. So it would be a limited but nevertheless very significant demonstration of flying an EmDrive vehicle. The reality is that any future application of a flying vehicle would really need Doppler compensation, and the only future applications that we see for second generation technology is really in the marine field, where accelerations can be extremely low, especially if you're talking about supertankers. So we've said that future flight applications of a superconducting EmDrive thruster clearly require Doppler compensation to enable it to have any reasonable acceleration performance. We've gone through the theory and the maths behind Doppler compensation, and it's probably worthwhile going back to our lecture 2 as a starting point if you need to go through this again. What we've said is that the Doppler compensation is carried out during a pulse. So we require pulse modulation first of all, and within the pulse we need to correct the transmitted frequency as the Doppler shift changes the frequency of the travelling wave inside the cavity. And as the frequency goes down, if you're accelerating in the normal direction, then you also need to correct the length of the cavity again during the pulse that we're applying. Now, to carry out the frequency compensation, the first thing we need to do is to be able to measure the Doppler shift itself. and we do this by using a classic radar technique, which is to employ circular polarization. If you use circular polarization to generate your transmitted wave, and then compare the reflected wave, the polarity of the reflected wave, you will find that they are opposite. And this provides a brilliant method of separating out your transmitted and received waves. And as I say, it's been used in radar technology for many years, very successfully. Incidentally, it was actually first suggested by a group of Chinese researchers who were looking into this particular problem for EmDrive operation. So if you look at the diagram of the thruster, you will see that there is a large input antenna with one polarization helix at the small end of the cavity, and this is your input antenna. So it transmits at one circular polarization, and then if you look carefully at the detector antenna, which is the small and the helix antenna next to the input antenna, hopefully you'll see that it's a different helix, or the opposite helix, to detect the opposite circular polarization of the reflected wave. We'll go through the circuitry that's used in this arrangement in the next slide. But we also need to look at how the length of the cavity is changed. And you can see that at the small end of the cavity there is basically a sliding section, and that section is controlled by a set of piezoelectric elements which provide the tiny extension that's needed, or the contraction that's needed, to control the overall axial length during the pulse. Interestingly, the precision that's available with this technique using piezoelectric elements is such that we can actually do real-time correction of any plate alignments that may occur due to thermal changes, actually during the operation of the thruster itself, which is a useful thing to be able to do. You can see that the cavity itself is a pretty short cavity because it's using only a single half wavelength mode. This reduces the Doppler problem to a minimum to begin with, and we've seen that from the maths of the Doppler shift. You may also notice that the substrate that supports the large end thin film is quite robust, quite substantial, and this is what we learned from our experimental thruster. You have quite high forces, internal forces created in the substrate during the operation of the thruster, and therefore this needs to be mechanically very robust. The cooler is mounted directly underneath the large end plate substrate, because clearly this is where the majority of the heat is generated, and this must be cooled quickly by the liquid hydrogen that is inside the cooling element. We've seen that a closed loop control system is necessary even on a first generation EmDrive thruster, basically to enable real-time compensation for thermal changes within the cavity itself. But for a third generation engine, the control system, which again is a closed loop system, becomes rather more complicated, and it's shown in this block diagram in this slide here. And to go through the circuit, we need to start in the cavity itself, and you can see that from the detector antenna, the detector output, which is a very small sample of the power inside the cavity, is fed directly into a microwave mixer. So we're using this mixer to compare the detector output with a sample, a very small sample of the input frequency, which is fed into the what's normally termed the local oscillator input of a mixer via a driver amplifier. So this technique of detecting the difference between the transmitted and the received signals is again a standard radar technique, perhaps slightly old-fashioned these days because it's an analog technique, and quite interestingly, the American solution to this particular problem was to do it all digitally. But what I'm proposing here is a straightforward analog system, which we've known as to work very well on radar systems. So the microwave mixer gives you a zero frequency output when the frequencies of the transmitted and reflected waves are the same. But as they start to change, you get a phase error. And this phase error comes out of the mixer and is fed directly into a control processor, which is where the magic happens, because the control processor then carries out the calculations necessary to provide a control signal into the signal generator, which is inevitably a digital synthesizer. So this is essentially how we control the frequency of the input antenna to match the Doppler shifted reflected frequency as measured by the detector antenna. If we look at the output of the signal generator, you can see that first of all it provides the sample for the microwave mixer. It then goes into a switching arrangement which enables another signal generator to be used if we have to employ the redundancy switching that would be available in multiple engine situations. You'll see how we do this when we actually look at vehicle systems. The signal then goes through a microwave power amplifier, inevitably a solid state power amplifier, before it's fed through a circulator to provide protection from the reflected powers during any mismatch situation that might occur, and then through a selector switch. And this is where we switch the input power from one cavity to another cavity to ensure that the power amplifier and the previous microwave components are actually operating in a CW mode. We've looked at this during the theory slides. The power then goes through an input tuner before it goes into the cavity itself via the input antenna. So the only other control function you can see in this block diagram is the signal that comes from the control processor into the piezoelectric elements, and these are DC levels that are fed individually to the piezoelectric elements to provide the axial length correction and any plate misalignments that might occur during engine operation. During our early work on third generation thrusters, we proposed a third generation spaceplane. Now, because of the limitations on third generation, this design meant that we had to have separate engines for the lift function and the horizontal acceleration function of the orbital engine. Essentially, this is the Doppler problem rearing its head again, and this meant that the lift engine itself, which was a 900 megahertz 8-cavity 2-axis gimbal engine, would have a specific thrust, quite a high specific thrust of 667 newtons per kilowatt, but the vertical acceleration that it would give would be limited to only 0.39 meters per second squared. To get the orbital velocity required, we proposed a fixed 1.5 gigahertz engine, and this would have a much lower specific thrust of only 185 newtons per kilowatt, but would enable an acceleration of 6 meters per second squared. The vehicle also carried 3 small C-band 2-axis gimbal thrusters, which would give roll, pitch and yaw control once it was in orbit. And the total launch mass for this fairly small spaceplane was estimated at less than 10 tons. Well, it was targeted at less than 10 tons and turned out on analysis to be 9,860 kilograms, allowing a 2,000 kilogram payload, a 2-ton payload. The airframe design was based on a US Air Force X-37B spaceplane, which enabled aerobraking and a glide approach to a conventional horizontal landing. To our knowledge, this third generation spaceplane was never actually implemented, but it provided a very good stepping stone, if you like, to our fourth generation considerations. The motivation for looking at fourth generation technology actually came from a series of reports that we received of the flight characteristics of so-called UAPs. These were unidentified aerial phenomena. Sort of started around 2017, 2018, and there was a gradual leakage of information about these sightings from all sorts of sources that was eventually confirmed by a US intelligence report, which was published in June 2021. And here they gave a strong indication that the UAPs were actually real, or some of the reports were actually real, and that they were definitely not of extraterrestrial origin. Now, this raised the intriguing possibility that these UAPs could actually be experimental UAVs, and the characteristics, the flight characteristics, corresponded very closely to what they would be if they were EmDrive thrusters. And this was actually suggested in an article in April 2021 of a US aerospace publication. The only problem, though, was that these UAPs really seemed to accelerate rather more quickly than we'd been able to predict for third generation technology. So we needed to look at a solution to this problem, and it was simply a challenge that I couldn't avoid rising to. So we had a good think about it and came up with a solution of short pulse modulation. We simply use a third generation type thruster, but increase the pulse rate and reduce the pulse length. I'd had discussions of this approach with US colleagues some years before, but I personally rejected the approach because it went against the grain to actually waste some of the wonderful power that we'd produced in our microwave system by modulating it with a fast square wave, which would cause the power that you're putting into the thruster to spread outside the very narrow bandwidth of the resonant cavity itself. So at first sight, there seemed to be a particular problem with short pulse modulation. And I've illustrated it by the spectrum that's shown in the slide. This is a spectrum of the 3.85 gigahertz signal that the flight thruster operates on. But in this case, we've applied a 1 megahertz square wave modulation, giving a pulse width of a pulse length, sorry, of 0.5 microseconds. If you look at the spectrum, you can see that there is a major peak shown in red that sits nicely between the bandwidth of the cavity itself, the 3 dB bandwidth of the cavity itself. But what you can see is that the two nearest sidebands are well outside the bandwidth of the cavity, and indeed the sidebands that are further out are also well outside. So what this means is that you are sacrificing some of this power that you've very carefully and very expensively generated by it being reflected back into the via the circulator into the load. So we needed to look very carefully at the effect of short pulse modulation. We said in lecture 2 that EmDrive operation is essentially the operation of a stored energy device. And it's this fact that actually gives us a solution to the short pulse modulation problem. And in fact, when I looked at this theoretically, it appeared that short pulse modulation actually increases the total stored energy level compared to the longer pulse modulation that we'd proposed for third generation operation. And we can see why this is by looking at the result of a theoretical calculation on the plot, and that this is comparing the theoretical stored energy for the flight thruster at CW and at 2 modulation frequencies. So the CW operation is simply at the 0.5 level, because we're only using half the total input power for one of the 2 cavities. The blue dotted line or dashed line shows what happens to the stored energy at 102 kilohertz modulation. And you can see this follows the same characteristic that we've seen for the 3rd generation operation. You simply get a an increase in stored energy over the first time constant. You switch off the power, and over the second time constant it decays exponentially to close to 0, and then the cycle is repeated again. However, if you then increase the modulation frequency by a factor of 10, and this is the red line, where we're modulating at 1 megahertz, condition is quite different. You can see that because the stored energy doesn't have time to dissipate, essentially, you get a staircase effect, and you build up the total stored energy to a higher level than it would be at a CW level, or indeed at a much lower operating frequency. The calculation showed that the stored energy actually increases from the 0.5 level for CW to a value of 0.887 for 1 megahertz modulation. This was a bit unexpected. So I'd never really thought of it quite like this before, but it was a great result to get, and one that the first thing we had to do, obviously, was to confirm this by measurement. So we took the flight thruster, the poor old flight thruster that's been through an awful lot of testing in its lifetime, and we carried out some measurements. And these are essentially shown in the table, where we're measuring the stored energy inside the cavity by basically measuring the detected power. And you can see that for CW, 102 kilohertz modulation and 1 megahertz modulation, the errors, are pretty small, just a few percent. So we were very pleased that in fact we had a solution to the acceleration problem of 3rd generation engines, and it was a very simple solution, really. We simply had to use short pulse modulation. Okay, to make sure that we're not kidding ourselves, that we're not actually getting something for nothing using a 4th generation EmDrive thruster, I decided to look at it in the typical engineer's fashion, look at the system efficiency of this particular mode of operation, to make sure, as I say, we weren't getting something for nothing. So we define the system efficiency as the efficiency of the EmDrive engine and the vehicle that it is accelerating. And we're looking at the output energy of this system, which is the energy, kinetic energy at the terminal velocity of the acceleration period, divided by the total energy that we're putting in over that acceleration period. And bear in mind, the acceleration period now for short pulse operation is very short. So we've said overall system efficiency is equal to delta KE divided by EM plus ES, where delta KE is the change in kinetic energy over this acceleration period. So that's the output of the system. EM is the mechanical energy that we're putting in, which is basically the force over the distance, which we've seen this equation before. And ES is the stored energy. Again, we've seen this equation before. So if you take this particular equation for system efficiency and plot it against pulse length, you get the blue dashed line that I've shown on the plot to the right. I've also plotted the acceleration and the thrust, and we've done this for an example of the heavy launch vehicle, which we'll describe in the next lecture, and we've taken it to an extreme velocity, constant velocity of 100 kilometers per second. And you can see that as you effectively decrease the pulse length and increase the thrust and the acceleration as you move down the pulse length horizontal axis, you don't get this increased thrust and acceleration for nothing. You get a decrease in the overall system efficiency. And this again is a good example of why the EmDrive concept basically follows the law of conservation of energy. You really don't get something for nothing.